This video is on nuclear particles and reactions. So this unit we're going to talk about nuclear particles, and the list of nuclear particles are in this box here. We have an alpha particle, which is a 4,2 helium, a beta particle, 0, -1e, a gamma ray, which is 0, 0, and the gamma symbol is an upside down Y. Kind of looks like the upside down cancer ribbon. A positron is a 0, 1e, a neutron is a 1, 0n, and a proton is a 1, 1 hydrogen. So these should look kind of familiar. Remember, we write these as mass number, atomic number, and then we have our symbol. Mass number, we remember, is protons plus neutrons, and the atomic number is equal to the number of protons. In nuclear particles, we are focusing on the nucleus, hence the word nuclear, which is why we don't care about charges with these. We're not worried about our electrons. We can have different types of radiation depending upon the particles that bombard us. We can have alpha particle radiation, which is the heaviest and slowest type of radiation. When you're exposed to this type of radiation, wearing clothing will protect you, but your bare skin can be affected. Beta particle radiation is faster and will penetrate your body. If you were to wear a lead sheet, like at the doctors where they put that lead coat over you, that would protect you from beta particle radiation. Gamma radiation is the fastest type of radiation, and it penetrates the furthest. For you to be safe from gamma particle radiation, you would need to have feet of concrete in between you and the radiation to be safe. When we go through nuclear particles and we bombard another particle with one, we have a transmutation. Here we change the number of protons or neutrons in a nucleus when a nuclear particle is absorbed or emitted, and we'll look at that more in a minute. There are 4 types of nuclear reactions that we can have. We can have natural radioactive decay, where a nucleus naturally absorbs or emits a nuclear particle to be stable. And we'll see what kind of elements end up doing this. We can have artificial radioactive decay, where a scientist goes and bombards a nucleus with a nuclear particle, causing the number of protons or neutrons to change. We can have fission, where a nuclei with a large mass is bombarded with particles that split the nuclei in 2, and therefore each new daughter particle will have a smaller mass. Or we can have fusion. Fusion, we have the nuclei of small masses, so 2 small particles will combine to form a larger mass nucleus. So fusion, we fuse 2 things together, so we make something bigger. Fission, we're going to split them apart into 2 smaller molecules, or 2 smaller atoms. So radioactivity occurs because of an unstable nuclei. Atoms that have less than 30 protons, so things less than zinc on the periodic table, need a ratio in their nucleus of 1 neutron to 1 proton. Anything with an atom that's greater than 30 protons or greater than zinc on the periodic table with atomic numbers, they need a ratio of 1.5 neutrons to protons. If an atom does not have this ratio already, they must either emit or absorb a nuclear particle to achieve this. So because this happens to get these preferred ratios, we end up with transmutations. Here, new elements are made based off of losing or gaining their protons and neutrons. So either new elements or an isotope. All elements after uranium are called the transuranium elements. All elements after uranium are made in the lab with force of nuclear bombardment. So we are actively making them in the lab. They're not found in nature. And we do this by taking those nuclear particles. So these particles here, we bombard any one after uranium with one of those to make a new one. So because of this, they are all radioactive. Now we can write these nuclear reactions. During this time, we need to know that the mass number and the charge are conserved. Now, our charge is our number of protons because we're just dealing with our nucleus. In our nucleus, we have neutrons and protons, so the charge of the nucleus is our number of protons, which is our atomic number. The mass number also has to be conserved, so we can't just make them disappear, we have to account for them. So they are either going to gain or lose their nuclear particles. So an example is that if sulfur 32 is going to decay into some new particle and is going to give off an alpha particle. So my bottom number is my charge has to be conserved. So I have 16 here, 2 here. So to make both sides equal each other, what plus 2 is 16? Well, 14 plus 2 is 16. I have to do the same with the top. I have 32 on the top, and on the right I have 4. So what plus 4 is 32? That's 28. I look on my periodic table to find out what is number 14. Number 14 is silicon. So the type of radiation here is alpha emission, because an alpha particle is emitted. So we translate this into words. Sulfur 32 decays via alpha emission into silicon 28. My second example, the opposite of my first. So my first example, I had emission. This time, I'm going to have absorption. I have my oxygen atom is going to absorb 2 beta particles and make something else. So this is bombardment. So my type of radiation is beta absorption. So here I have 8 and 2 of my beta particles. That means my charge at the bottom is -2. So 2 times 1 is -2. 2 times 0, still 0. So 8 minus 2 is 6. So on the right, I also have to have 6 for my charge. On the left, my mass number is 14 plus 0 is still 14. And I look on the periodic table, number 6 is carbon. So to translate this into words, oxygen 14 absorbs 2 beta particles to form carbon 14.